So let me introduce our second speaker. Chauvin is based in Cambridge, is a postdoc in Professor Cooper's group, and today he's gonna give a talk on density matrix renormalization group for continuous system. Chauvin, the audience is yours.
Thank you so much for the introduction. So Hannah just gave a talk about a very nice discrete system, and some of you in the audience might already know that if you have a strongly interacting discrete system, particularly in 1D, then a very efficient computational method to accurately find the ground states as well as time evolution is density matrix renormalization group, which is in short form known as DMRG. So what I'll try to do is tell you about a newly developed technique to apply DMRG to continuous systems in a versatile and practical way. So there's a generalization of DMRG to continuous systems. And this work was done with these good people here. And as you can see, we are trying to put it on archive sometime next month, but that's just a target. Okay, so just a very brief overview. The way DMRG actually works in a discrete setting is that it efficiently truncates the many-body Hilbert space based on the local entanglement to a manageable size so that you can get the ground state as well as time evolution in polynomial time, rather than exponentially diverging with the system size. And so in the modern formulation, what you do is you write the many-body wave function psi as a product of these matrices, and you treat the elements of these matrices as variational parameters. And you can see two types of indices. The sigmas are the physical basis states like spin up, spin down. And the B's are what are called auxiliary states or bonds. And the dimension of these bonds control the degree of entanglement in the state. So typically what you do is you optimize the matrix elements 2 matrices at a time, and you sweep left and right through the system, and you increase the bond dimension of these B's as you need to converge to the ground state or the time evolving state. So that's how it usually works. And it produces very efficient results. And so people have, unsurprisingly, tried to apply it to continuous settings. But the punchline here is that it remains a key challenge despite these attempts. So here are some of the attempts. So what you can try to do is simply discretize your continuous system on a grid and then apply DMRG. But if you do that, this approach converges very poorly with the number of grid points, and sometimes actually it does not converge. It can get stuck in some local minimum if you have multiple length scales in your system. You can also try to derive a continuum limit by taking the grid spacing to 0. And in that limit, you get a field theory formulation, which is known as CMPS. This has had some success for homogeneous systems where you have translational invariance. But as soon as you have some inhomogeneities, you break translation invariance, it becomes impractical. So these are the key challenges. On the other hand, there are no shortage of open problems on continuous quantum systems, and these are a sampling of some of those. And you might have your own favorite continuous quantum problem. Okay, so this is a way to tackle this challenge. And the main idea of our approach is quite simple. So instead of discretizing it on a set of points, we divide the system into a bunch of segments. So these need not be, we're not talking about the limit of vanishingly narrow segments, but you can have finite segments. And we use continuous basis functions inside each of the segments to model the local physics. And so if you use this sort of partitioning, then you can map the Hamiltonian into a discrete sum over these segments. And then it looks just like a Hubbard Hamiltonian. So in this partitioned form, you can actually tackle the Hamiltonian directly using existing DMRG routines. So that's the main idea. And we have tried applying it or benchmarking it to prototypical cases. So for example, if you have bosons with contact interactions with or without an external potential, then it produces reasonable results. So it reproduces known limits, which are these, and you get fast convergence, which can be controlled to some extent by how you choose the basis functions. And we also find a Superfluid-Mott transition in a shallow lattice, which is not accessible by tight binding approximation, for example. So I'll mainly talk about these idea and application part, but I'll also mention that you can, the technique can be straightforwardly generalized to other settings. For example, if you have fermions, you can treat them on an equal footing as bosons. And you can also think of mixtures like Bose-Fermi mixtures or long-range interactions and so on. And one should plausibly, should also be able to extend this for time evolution using these known techniques such as time-dependent variation principle. Okay, so here's just a flavor of how it actually works. So I take a model Hamiltonian describing interacting bosons. I'm sure most of you have seen this Hamiltonian. So there's a kinetic energy part or a single particle part, and there you have the interaction part with some interaction string, contact interaction string G. And let's say we are interested in finding the ground state of the system confined to a box, which I take between 0 and 1. So the idea is that you partition this field operator psi x in a bunch of segments. So L segments, which are indexed by this number G, by this index J, sorry. And the square here is just a box function. So it is 1 when x is between these limits and is 0 otherwise. So it's just dividing psi into a bunch of segments. If you substitute this into the Hamiltonian and take care of the delta functions arising from this discontinuity in the box function, then you arrive to this formula. So you see that I've turned H into from a continuous integral to a discrete sum over these segments. And these Kj and Ujs are just the kinetic energy and the interaction energy in the jth segment. And then there is this term. And if you look closely, this difference here is just the difference just to the right of xj and to the left of xj. So this is measuring the discontinuity at the boundary xj. And this is the same term conjugated. So this is actually a positive semi-definite measure of the discontinuity. And lambda is like an energy penalty, which is formally infinite. So it means that in the ground state, this term has to vanish because otherwise the energy will just blow up. So that means in the ground state or in any low energy state, you won't have any discontinuity, which makes sense. Okay, so now the Hamiltonian just looks like a Hubbard Hamiltonian. You have these local terms, which are like the on-site terms, and you have the nearest neighbor terms here. So if I take xj plus, that is in j plus 1th segment, and xj minus is in jth segment, so this is like a nearest neighbor coupling. And so you can apply traditional DMRG on this once you have expressed these operators as matrices. That's all there is to it. And how do you take care of lambda? Well, we found the easiest way was to just increase lambda in steps so that the discontinuity goes down as you optimize your parameters. Okay, so the only difference from what you have typically in a lattice system is that these segments are not only points, but rather continuous patches of space. So instead of having Fock states on the grid points, the local basis functions are now a set of continuous functions. Okay, so for example, here is one segment, and I choose there can be a bunch of these single particle basis functions. Similarly, you can have 2-body basis functions, 3-body basis functions, and so on. And of course, you have to truncate at some point. So these are examples of the basis functions. You will notice that there's a kink in the 2-body basis function here. And that's because we know that this contact type of interaction will give rise to that kink whenever 2 particles come at the same place. And so we have specifically chosen basis functions which has that kink built in. So this is a way to optimize basis functions to get the efficiently find the ground state.
Chauvin, you have 2 minutes plus 3 minutes of questions.
Great. I'll try to finish. Okay, so that's the main formalism, and then I'll just show examples. So this is a case where you have 5 particles in a box, which is divided into 8 segments. And there are some strong interactions, which is this gamma parameter, which is equal to 50, some large value. And so as you see that as I increase the penalty for discontinuity in steps, which are these different parts here, these grid lines, then you see the discontinuity goes down monotonically, and the continuous part of the energy approaches the exact known energy from beta ansatz. Okay, and actually the error, which is the difference between this extrapolated energy E star and the beta ansatz energy, is already 1 in a million with 8 segments. So this is quite efficient. These are the ground state density and correlations that you get out of this. So, these vertical lines are showing where I have the boundaries between segments. And you can see that I get a smooth function for the density and correlations, which are close to the Tonks limit of infinitely strong interactions, but quite far from a mean field approximation, which is this Gross-Pitaevsky equation. Okay, this is a comparison with discretization on a grid. So you see the error for discretization goes down as 1 over L squared, where L is the number of grid points, whereas in our case, it goes down as 1 over L to the 6. And this power law actually depends on the basis. So here I've retained all cubic monomials in my basis function. So cubic variations are captured. And that's why it's 1 over L to the 6. If I have mth degree monomial, then the error will go down like this. But of course, if I increase my basis size, that also adds to the computation time. And so if you look at the computation time versus error, then there is still an improved power law, but you get the advantage at small errors. At large errors, you can get by with discretization with less time. And it's also more efficient with stronger interactions where you have the probability of having more particles at the same place is reduced. Okay, I think I'm out of time. So this is just an extension application to the inhomogeneous case. So here you see some shallow lattice, V is equal to 2 ER, 2 times the recoil energy. And as I increase interactions, the state becomes more and more localized and the correlations become exponentially decaying. So this is superfluid, this is Mott. Whereas if I have a strong lattice, then that already happens at relatively small interactions. So gamma is 1 is enough here. Okay, I think I won't go to the details here. So this is just to show that we retrieve the known limits. So beta ansatz, Tonks gas, as well as tight binding for deep lattices. It agrees with those limits. And you get superfluid to Mott transition, although in a finite size system, but you see that the condensate fraction goes down as I increase the lattice depth. Okay, I think I will conclude without going into further details. I'm happy to answer any questions. So this is a versatile practical way of applying DMRG to continuous setting. And I've already told you the advantages. And I'll just mention that the next step would be to apply this to interesting problems and to extend these to these out of equilibrium or other physical settings. I want to advertise that one of my colleagues will give a talk at 2:20 on first order phase transition in a shaken lattice, where I was also involved. So thank you very much for your attention.
Thank you, Chauvin. Yeah, probably the talk of your colleague would be slightly later because we're a bit late in the schedule. Any question for Chauvin? Maybe can I ask a quick question? I'm not really an expert on these, let's say, quantum models, but if I got right, all the examples that you've shown are 1D examples. So does the idea of the code also work in 2D or 3D?
Yeah, in principle, the mechanism of spatial partitioning to turn into a discrete sum is also valid in 2D. And so it will depend on how the discrete sort of DMRG codes already available in 2D works. You have to just adapt those to this discrete sum. So for example, in 2D, there are generalizations of DMRG like PEPs, but they have more complexity than in 1D.
Thank you. I can see that there's also another question by Anand, but we're running a bit out of time. So maybe if you can maybe just reply to the question on the chat, please. Thank you.